Hello, welcome back to my YouTube channel. Today I want to solve a number theory problem from BMO 2015. So, what the problem said, we have 20 consecutive positive integers and we have to prove that there is an integer d such that for every positive integer n we have the following inequality: n square root of d, fractional part from n square root of d is bigger than 5 over 2. So, it isn't easy. In that year it was a fourth problem, but we have to look on some particular things. So first of all, when you see 20 consecutively, you have to think of 5 and you have to think of 4. Okay? 5 and 4. Of course you have a number which is divisible by 20, but it is not that case. We don't need that number. So we look at 5, we look at 4, but we take it to be congruent with 0 modulo 5, and with 4, well, with 4 we have a very nice thing here. So take it fractional part. Let's return in the next manner. So it's the number minus the floor function. Okay? We have something like this. Okay? And we can do the next thing. So multiply by the conjugate. So we have n square d minus floor function at square, which indeed is bigger than n square root of d over n square root of d times 2, because the floor function is more than n square root of d, and when you take the inverse it's going to be opposite sign. So here you have something like this. So here you have a very good thing, because let's clarify this stuff. So you're starting from floor function and square root and reach this good position where all of these things, all of this stuff are natural numbers. Look, we have something to do to work with this. I will not say that we cannot improve this inequality, because look, we have equality here, but in the original conclusion we have strictly, but we don't say nothing about d. So let's start to put some context. So I have here a number minus a perfect square, and we have the idea to take something modulo 4 and you have a square. Yeah, that's right, you have to think of this property. So if you have a prime number which is congruent with 3 modulo 4 p prime, and p divides m squared plus t squared, yes, that's right, p divides m and p divides t. Also, if you take some number which is going to be congruent with 3 modulo 4, I think it's clear that it isn't perfect square. So let's put it this context right right here in the next manner. So let's put d congruent with 3 modulo 4 and d congruent with 0 modulo 5. Right now, n square root of d is irrational. So with this thing in mind, here you don't have equality. So here is strictly, because here this stuff is not n square root of d. So you will reach this destination. So right now with this condition we can say something like this. So we have n square root of d times fractional part n square root of d, yeah, is bigger than n squared d minus floor function n squared d over 2, which right now we can put equality 5 over 2. So we have to prove that this stuff happened. Right now, maybe you think, okay, with 4 maybe there are some things that it's coming in mind, but with 5 it's like a convenient way to do it, but also you don't have a really motivation. But right now we have, because we want to cancel some cases. So first of all, it's clear that this stuff is not perfect square, so n squared d minus this floor function is not 0. Also, if d is congruent with 3 modulo 4, it will be a prime q congruent with 3 modulo 4, and let's written like this: if n is floor function plus 1 or plus 2, from this stuff and the property written sometimes ago, it will be arrived at q divides 1 or q divides 2, which is false. So right now, n squared d minus n square floor function n square root d, we can cancel the case 2 or 3. And right now 5 came, because if 5 divides d, and if n squared d is this stuff, in this particular case it's going to result that this number, this square number, is going to congruent with 3 modulo 5, false. And if n squared d is floor function, it's going to result that this number is congruent with 2 modulo 5. Again, false, because we don't have a square to given the residue modulo 5, 2 or 3. So right now, with our choice, n squared d minus floor function, it cannot be 0, 1, 2, 3, 4, so it's less 5. And right now we're done. Difficult one, but we can underline some motivation of choosing D. I hope that you like it. Please try again. Try to understand all the arguments. If you have questions, write in the comments. I hope that you like it. See you next time. Bye bye.